In this tutorial, we will be discussing the valence bond theory and an introduction to hybridization. The valence bond theory is involving the overlap of atomic orbitals to form bonds. It uses the Vesper model, which, as you remember, is valence, shell, electron, pair, repulsion. So we're talking about the interaction between the valence electrons and bonds. The valence electrons in an atom reside in the quantum mechanical atomic orbitals or hybrid orbitals. What it's referring to here is the s, p, d, and f orbitals. And the electrons must be spin paired. So that's referring to the m sub s, where one arrow is going up and one arrow is going down. A chemical bond results in these atomic orbitals interact or overlap, and there is a total of 2 electrons in the new molecular orbital. When direct overlap of the atomic orbital cannot or does not explain experimental finding, then hybridization of the atomic orbitals on the center atom occurs. So we're focusing on the center atom, the s, p, d, and f. The shape of the molecule is determined by the geometry of the interacting orbitals. The electron geometry of the molecule or ion dictates the hybridization of the atomic orbital on the center atom. There is a problem here, though. It cannot explain bonding with molecules or ions bringing in an odd number of valence electrons. Electron configurations of each of the atom's valence electrons for H2S are as follows. We have 2s2, 2p4, and then hydrogen is 1s1. So the electron orbital here are being shared with the hydrogen. The Lewis dot structure and the distribution of hydrogen's electrons in sulfur's atomic orbital coincide with the atomic orbitals of the hydrogen atoms. So the 1s orbital overlaps with the 2p, as you can see right here, to make 2 electrons spin in opposite directions. That's the signification of the arrows going up and down. The atomic orbitals on the s atom, the sulfur atom, which is the center atom, can accommodate the 1s atomic orbitals from the hydrogen atoms without any need for hybridization. But sometimes you do need hybridization. As we said before, if our theory does not match what we have experimentally, then we need some form of hybridization. Hybridization is the mixing of the center atom's valence electron atomic orbitals. So once again, we're really looking at the center atom's s, p, d, and f orbitals. It arises when the number of partially filled or empty atomic orbitals of the center atom did not predict the number of bonds or orientations of bonds between the center atom and the other bonding atom that actually occurred. Here's an example, is carbon and hydrogen. If we look at what we actually have here as far as the Lewis dot structure, we have 2 p orbitals with half filled, and then nothing in the last one. So according to our overlap theory, we would need a hydrogen here and a hydrogen here, and there would be no need for one here because there's nothing in it. So there is no overlap. So in theory, we would only have 2 bonds. But what's actually happening is we're forming 4 bonds. So we needed an explanation as to why that occurs. And the explanation is that it's hybridized. To explain inconsistencies, it was postulated that the valence atomic orbitals of the center atom could hybridize before bonding took place. So what's happening is we have 1 2s orbital and 3 2p orbitals that are blending together to form 4 total hybrid orbitals, sp3. So when we talk about sp3 hybrid orbitals, there's a total of 4. 1, 2, 3, 4. The easiest way to remember that is we have 1s and 3p. When we add those two together, it comes up with 4. So we have now 4 spots for those electrons to go into, which then better explain what we see in the molecule, because we know that carbon exists with 4 bonds. And so now we have a spot for every single one of those hydrogen atoms to go. Don't get wrapped up in the mathematics of it, but look more at the number of orbitals and the number of bonding electrons, bonding groups. So here we have the 1s orbital, and we're adding the 3p orbitals, and we're blending them all together, and it's forming these 4 hybridized orbitals. So we have, it's basically making a big loop on one side and a small loop on the other when they overlap. And the big loop is where the actual overlap is going to go. So before I mentioned that the orbitals add up to the number of electron groups. So if we see here, sp, we have s1, p1, we have one s orbital and one p orbital. We have a total of 2 electron groups. Trigonal planar, we have one s group and 2 p orbitals that are overlapping, for a total of 3 electron groups. And we can keep going. For tetrahedral, let's just say 3 here. There's 1 s group, 3 p groups that are overlapping to get 4. That is a misprint in the book, so make sure that says 3 there. Trigonal bipyramidal, 1s, 3p, and 1d for 5. 1s, 3p orbitals overlap, and 2d orbitals overlap for a total of 6. So notice the number of orbitals that are overlapping are going to equal the number of things coming off that center atom. So if we look here and try to figure out what the hybridization is of every single one of these, we can look at how many groups are coming off it. So for instance, this would be sp3 because there's a total of 4 groups coming off. That carbon will be sp3 because there's 4 things coming off of it. This carbon here, however, has 1, 2, 3 things coming off it, so it'll be sp2. And then this oxygen has 3 electron groups coming off, so once again, I'm sorry, 4 things coming off of it, so once again it'll be sp3. And that's how you do valence bond theory, and just an introduction to hybridization.